Everyone, welcome to the GDS Agent for Graph Algorithmic Reasoning session. You're here with the speaker, Brian Shi. Over to you, Brian.
Yeah, thank you, Matt. So, hi everyone, welcome to Notes 2025. This session is about GDS Agent for Graph Algorithmic Reasoning. I'm Brian, I'm a senior software engineer at Neo4j, working in the graph data science team. I work on graph machine learning and graph algorithms inside GDS. And more recently, we are also looking at ways of using techniques from graph ML and graph algorithms to make LLMs work on graphs better, which is what we'll discuss today. So brief agenda, I will introduce what is graph data science. I will also introduce what is the agentic framework that we are talking about. And then we'll go straight into a demo of the GDS agent. We'll look at how it behaves on some real-world use cases. And afterwards, we also share some benchmarks and some findings that we have, as well as future works that we have in mind for GDS agent. Okay, so let's get started. So hopefully everyone knows graph data science is a library on top of the Neo4j database. So for Neo4j, there's a database and it comes with the Cypher query language. And the key ingredient of it is pattern matching on graphs, which allows any user to retrieve relevant data that you want on the database. So here is one example of a Cypher query. You can write some match statements of one-hop neighborhoods between nodes. You can add the constraints on the labels of nodes and relationships. You can add filterings of your patterns, and you can return specific properties as well as do transformations on the properties. But Cypher itself doesn't really cover all the use cases that someone wants to have on the graph data, right? So you might also want to run graph algorithms or machine learning workloads on your Neo4j graph, and that's where GDS comes in. So it has a comprehensive set of algorithms on top of the database, for example, centrality, community detection, path finding, and node similarity algorithms. So how do you actually use GDS nowadays? So the first thing you need to do is to project the graph from the database into memory via Cypher projection. And the way to do it is first you would write some Cypher statement to define your graph, or possibly a subgraph from the database. And then you pipe that to a call with gds.graph project, okay, with a name that you come up with for the in-memory graph, the source and target nodes, the relationships, and also relevant properties on nodes and relationships that you would like to project. After you can project multiple graphs on the same database, and afterwards you can take those in-memory graphs and call algorithms on them, right? So here is an example of calling PageRank on a projected graph with the name myGraph, with some particular parameters which you choose to have. And here is another example of calling price collecting Steiner tree on a different projected graph with another set of parameters for the specific algorithms. So this is what everyone does with GDS nowadays. Okay, so let's jump ahead a bit to looking at what agent is. So everyone is already familiar with agents from many other sessions in Nodes. So here what we're talking about is letting LLMs decide what tools to use, right? So traditionally, if you use a single LLM, you can feed in a bunch of text and it will generate text based on the input. But more complicated workflows would equip LLMs with data, for example, through retrieval augmented techniques by retrieving relevant subgraph from Neo4j, textualize the subgraph and feed it to the LLMs. Okay, and more recently, people start to equip LLMs with tools so that based on some user prompt, the LLMs can decide what tools to use. They can execute the tools against the environment, in this case, Neo4j database, receives the feedbacks of the tools, which are usually results from retrievals or from algorithms, and decides what to do next, which possibly could be invoking other tools. Okay. So this is the concepts of an agent, and how do we actually build an agent? One of the ways is to adopt the model context protocol. So it is a standard protocol which allows you to expose all kinds of different software tools to an LLM, which is acting as an MCP client. So we built an MCP server containing a bunch of graph data science algorithms as tools, and we add the MCP interface to all of these tools. When the server is running, any MCP client can call those tools. So for example, you can have an LLM which would generate the structured outputs following the model context protocol. It automatically calls the tools, and it's able to see the results of the tool execution. Okay, so this is basically the introduction of GDS and agent. And let's just think a little bit about how they actually come together and why building GDS agent. So for GDS, what it's good at is that it is a large comprehensive set of algorithms and ML tools that we know are very parameterizable, and they are tested and correct, and they are extremely scalable. But at the same time, it requires some domain knowledge and understanding of graph algorithms, which comes as some barriers to actually start getting value out of it. LLMs, on the other side, are great at natural language understanding and reasoning capabilities in text. However, they have their fundamental limitations, right? So they cannot access private data on their own. And we also know that they cannot reliably compute graph algorithms on a large knowledge graph. So for example, if you describe an extremely large graph in text and send it to the LLM, and you ask it some questions of computing graph algorithms, it's not able to reliably give you the answer. Okay, so that's the bottlenecks the LLMs have. And it comes together because by building GDS agent, we remove the barriers of using GDS, and at the same time, we enhances LLMs with graph algorithmic reasoning power. So this is the GitHub link of the MCP server of the agent. And let's go into a demo. So here is a database that I have that is running locally on my machine. It contains a version of the London Underground map. As you can see, there are here 302 stations and 812 connections between the stations. And we can see each station have all kinds of different properties. For example, there are names, there are numerical properties such as longitude and latitude, IDs, and there are other integer properties such as total number of lines and the zone that the station belongs to. Okay, and then you can also look at the different links on the connections. And you can see that there are properties on the links as well. For example, you can see there's a distance, there's a line, and also a time, which represents how long it would take to travel between these two stops. So this is the data set that we are interested in. And we would like GDS agents to help us answer any questions which requires a graph algorithm, right? So here is my Claude desktop, which is acting as an MCP client. So I equipped it with the MCP server that's containing GDS tools. And the setup is easy, so you can edit configuration, and you add the 2 lines in the configuration, and UV will know that it needs to pull a GDS agent from PyPI and fetch and install and start the server. You also need to give it credentials to your Neo4j databases, such as the URL, username, and password as well. Okay, so what kind of questions can we ask to the agent? So one example could be that, say, I have a transport network in my database, so that you let the agent know that you're interested in your local data. And I ask, what are a few quickest ways to go from Paddington to London Bridge, which are 2 nodes in the database. Okay, so the LLMs inspects all the available tools, and it decides to first call a few auxiliary tools to help it understand the schema of the database. So for example, you can see that it's calling get node labels to see what are all the available labels in the database, get relationship types, get node property keys to find out all the available properties on the nodes, similarly the properties for the relationships. And then it realized that my question actually would correspond to an algorithm called the Jens k-shortest path algorithm. And therefore it would call the Jens shortest path here, okay, with this set of parameters. And you can see that the raw responses from the tool as well, which are the raw responses from the GDS library, which you can also check yourself that the data is correct and corresponds to what is in the database. Okay. After that, LLM takes the output and parses the information and can provide you a short report of what you're asking. So it gives me a few quickest paths. So it tells me the fastest route is along these stations, and it tells me the time it takes to go between each stations, and also tells me an alternative route as well. So it's worth mentioning that the parameters and the two invocations are entirely decided by the LLMs, right? This is the agentic way of using these tools. So for example, it decides to use k equals 5, right? And for users who are unfamiliar with Jens, so k is the number of top few shortest paths which you want to find. It also passes in the source and target nodes, which is the stations I mentioned. It also passes in the parameter which identifies what is the node property that these source target nodes corresponds to, and we know that they are the name of the stations. It also chooses to use a relationship weight property, which is time, instead of other possible properties such as a distance or line, because that is how the LLM has interpreted the word quickest in my question. If I would have asked a few shortest ways to go between the stations, then it might have used a different constraint. For example, it would have used a distance in the relationship weight, right? Of course, these are not the only questions that you can ask. You can also try other kinds of questions, such as this one. So I can say, is Embankment or Waterloo a more important station? Okay, and this is a rather vague question because I have not really defined what I mean by important. So the agent needs to try to understand my intent and look through all the available algorithms to try to provide me a report of an analysis and report of which station is more important. Okay, so it looks at the algorithms and it tries to understand what I'm getting at for being important. I decides to call degree centrality, returning the degree centrality of these two stations. It decides then to call between the centrality again for these two stations. And it decides to call PageRank for these two as well. And afterwards, it gives me an explanation. So it concludes that Waterloo is more important, and it backs up with the statistics it finds from the algorithm results. So for example, it says Embankment actually have more connections between the centrality. However, Waterloo is 10 times more important by this criteria and some analysis on PageRank, and therefore it gives a conclusion on that. It also explains to you what different algorithm means. For example, between it says that it measures how often a station lies on the shortest path of any other pairs of stations, which actually is the definition of between the centrality. Okay, let's try yet another question. For example, I can say, can I travel between every pair of stations in this transport network? And then it decides to use Jens. It decides to execute the weakly connected component. Okay, and it calls the algorithm, and it finds out that all the nodes have component ID 0. It then counts nodes to see that there are 302 nodes in the database, and it does a simple reasoning that all 302 nodes belongs to the same component ID 0. Therefore, every station is connected to each other. Okay. However, you can also challenge that. So you can say, I'm not sure that we can ignore the direction for WCC, weakly connected component. And I think it's possible that there is a connection from station A to B, but not from B to A. And I want to know, is it still the case that we can travel between the pair? Okay. In this case, the LLM understands what we're talking about, and it says it should actually call the strongly connected component, which would take into account of the directionality. And it does that, and it does process the results and concludes that still you can travel between any pair of stations, even considering that. Okay. So it's worth noting that for the entire demo, nothing is hard-coded against that specific database. As we can see, the LLM decides to inspect the database with auxiliary tools and interact with the data and responses and decides what to do next. Right. So here is a recap of the example workflow. or we ask it a question, for example, a few quickest ways to go between two stations, and we have a database running with the data. The LLM will call, for example, get node properties and relationship properties to inspect the database, and then it will call particular algorithm, in this case, Jens. Under the hood, it will first go to the database, projects the relevant subgraph, and it's going to call the actual algorithm on the relevant subgraph and return the data streamed to the client. And the LLM is able to parse the information and return the information to the client. However, we are interested not only in just trying out some questions and on Claude and just have a feeling of how it does. We want to also have some benchmarks so that we know if there's any consistent behaviors or findings that we can see. Okay, so we came up with a set of benchmarks ourselves where we write questions that implicitly require graph algorithms, and we also write all the expected tool calls and expected tool parameters, as well as final answers. So this is one of the example, which we've shown also in the demo, that assuming every link between stations go both ways, can we reach any station from any other station? And we assert what are the parameters and answers we need to have. Okay, and we ran this with a Claude model, Sonnet 4 2025-0514, with the GDS agent MCP server 0.5.1. On this benchmark, and the benchmark contains about 45 such kind of questions and answers. And here are the results that we have. So the first 4 parameters inspects whether it's calling the correct tools and passing in the correct parameters. And the final answer match measures whether the final answer is correct. Okay, so without going into the details, we can see the numbers for 2 invocations are in the high 70s and 80s, which means most of the times the LLMs is able to call the necessary tools, and it doesn't call many unnecessary redundant tools, and it's passing in all the parameters correctly, right? And we can see about 66% of the times for these set of questions on the on-the-ground database, it's able to give the exact final answer correctly. And more details you can find in this archive paper, which also contains the setup. Okay. We're also interested in the same benchmark with the same set of tools, but on different LLMs, so that we see something that is more generalizable. And here is the same benchmarks being run on 4 other different LLMs, so 2 GPT models and 2 Claude models. And you see that actually even different frontier LLMs exhibit quite different behaviors. For example, we can see GPT-5 is having a significantly higher score in obtaining the final answers, up to about 85%. And it's able to do this probably because it's got extremely high tool recall, so 93%. So it means it always calls the necessary tools, even though its precision is slightly low. That is that it sometimes calls redundant, unnecessary tools. So, but that doesn't seem to have an effect because we see GPT-5 excels at giving us the correct final answers. Okay. And after that, on top of that, we want some even more generalizable insights, and also try to stretch the agent to see whether when it starts to fail or times that it starts to struggle. So we took another data set, which is a version of the Game of Thrones data set, involving, for example, kings and knights and belonging to different houses and being involved in the different battles. And here you see it's a graph with many different node types and a lot of relationship types, as well as properties, and therefore extremely heterogeneous, which poses more challenging to the LLMs and to the agents. And we ran similarly those types of implicit graph algorithmic questions on this Game of Thrones dataset, and we measure how well did the frontier LLMs do. And in this case, you see that even the best LLMs sometimes start to struggle, right? So GPT-5 is still the best, being able to answer about 50%, about 60% of the final answers correctly. However, some of the other models just start to struggle when faced with this medium-sized heterogeneous graph. Okay, so finally, some summary for what we have covered. So GDS agent allows any user to solve complex graph problems that implicitly requires graph algorithmic reasoning. It removes the barriers of starts using GDS, as we can see, any users can start to ask questions to the LLM, and LLM is able to help you use GDS, also provides an explanation of why it does that, right? So you can check whether it's calling the correct algorithms afterwards. On the other hand, enhances the LLMs with graph reasoning capabilities, which it lacks without using GDS. Setup is convenient. It's just a two-line change in the configuration. And right now it supports GDS plugins for on-prem AuraDB, or on-prem AuraDS, and also AuraDB with GDS plugins. And of course, it can be used together with all the other MCP servers. And the user can collaborate with GDS agent to get started solving your problems. Okay, and some future work that we have is to support Aura Graph Analytics, which is the serverless offering for any Aura instance on the backend, and also to improve the reasoning capability on the most challenging tasks on large and heterogeneous graphs. With that, maybe I can do another quick question on a more complex task, which requires a lot of steps for the agent to solve. Okay, just to illustrate how you can collaborate with the agent further instead of just a single shot, one question and one answer, right? So here is a much bigger task. I'm telling the LLM that all the stations currently have zones assigned to them, but I want to create another set of zone systems for them by putting them into 5 different groups. And I want each groups to be well connected from within. Okay, and I also want the agent to explain to me why they choose them, the parameters and the algorithms, and suggest to me alternatives and how they differ to each other. So this is a much bigger task of trying to come up with a system of assigning zones to stations. Okay, and then it starts to try to clarify the requirements that I have and invokes multiple different community detection algorithms. Okay, for example, Leiden, modularity metrics. And at each step, it will look at the results. For example, sometimes seeing Leiden produces too many communities, modularity has parameters that's too specific, and Louvain also producing too many communities, and starts to iterate on that. And finally, we're able to give you a short report at the very end. Okay, so here you see that it's able to, in the end, come up with 5 well-connected communities after trying different things and gives you a recommendation. And of course, you can follow up with that with even more clear requirement or changes of what you want to ask. And it's able to work with you to explore other algorithms to run. With that, I think I will end it here. And here is the acknowledgements to all the people who have contributed to this project, to the code, the benchmarks, the papers, as well as all the content of the deck and the discussions. The QR code is for the GitHub repository, which I have linked earlier. It contains the MCP server, which you can set up and just get started today. For any questions, you can raise a GitHub issue at the GitHub repository, or also email either myself or email the GDS team. And that's it. Thank you, everyone. And I see there are some questions in the chat.